in this segment, we're going to look at the frequency up to which a MOSFET can operate. And we'll call this the cutoff frequency. So we need to think about our MOSFET and sort of build an equivalent circuit around it first. So let's draw a physical structure. Here's our metal, our oxide, and then our source and our drain. And then we have this P-type wafer out here. So we can start to think about the different types of circuit elements that this structure represents. So clearly there's going to be a capacitor representing the metal oxide semiconductor structure, but there's also some so-called parasitic capacitances between the source and the drain, the source and the drain and the gate metal. Also, there's resistances associated with both the source and the drain. In general, you can have leakage through the oxide, although design would be such that this is minimized. And then we need to represent somehow the nonlinear behavior of the channel. We're thinking about here an inversion mode P-body MOSFET. So we can use a little diamond symbol to represent the transconductance of the channel. So all of these different capacitances and resistances can be pulled off of this, this physical structure and then put into an equivalent circuit model. So let's start to examine that. Okay, so now I've drawn the full equivalent circuit which corresponds to this physical picture. So there are some extra capacitances and resistances put in here. So I'll label some of the important ones. So the source and the drain parasitic resistances, those will come from the resistivity of the actual implanted or diffused regions themselves. But then also remember that there's a specific contact resistance whenever you put a metal in contact with a semiconductor. So this interface can also contribute to this lumped drain or source resistance. It turns out that the drain resistance is the more important one here. There's above threshold, we've assumed that we're operating above threshold and that we're operating in the common source configuration. So what that means is both the body and the source are hooked to ground. There's the capacitance of the gate and source, the capacitance of the gate and drain, and both of those at threshold. And then here's our transconductance of the channel here. Then we've also added a parasitic resistance, which means that there could be some current flow from the source to drain even before we reach full inversion. And what this kind of represents is sub-threshold conduction. Then because both of these sources and drains are surrounded by a depletion width, because there's a PN junction running along this axis and this axis, there's also some parasitic capacitance coming from those parts too. So what we need to do is look at this circuit and then figure out what are the important parts and what's going to cause our limitations on how fast we can operate this device. So the first physical effect that one might envision is that there's a limitation set by how long it actually takes an electron to traverse this distance, which is the gate length L. So if you work out some round numbers, let's say L is about 1 micron, and we assume that the carrier is traveling at its saturation velocity, which is about 10 to the 7th centimeters per second, we end up with an estimate that the time it would take for the carrier to traverse this distance is something like 10 picoseconds. And if you flip that around, that turns into a frequency limitation of 100 gigahertz. So it turns out that this is not the limiting effect. This frequency is much, much higher than typical cutoff frequencies for MOSFETs. So we need to look deeper into the effects that happen because of this circuit. So on this side, I've drawn a simplified portion of this, and we're going to explore first the impact of source, or I could also put the drain resistance on the effective voltage which is dropped across the channel. So remember we're talking about a common source configuration. So our source is grounded, and all of our voltages are then with respect to the source. So our gate voltage is this big here. However, because of the presence of a source, or if you flip the MOSFET around like this and switch the source and drain, you could consider the drain resistance too. There's going to be a reduced voltage applied across the channel. So this VGS prime represents this voltage drop that's across the inverted channel and is embodied here in this transconductance. So the physical action of the presence of a source drain resistance is going to be to sort of rescale the voltage axis, the drain source voltage axis. So here's our current, and we might have a curve that looks like this. And if we look at this diagram, the portion from here to here is essentially a voltage divider, and so instead of being at, say, this operating point, you're really back at this operating point. So this is VDS, and this is VDS prime. The transconductance is not changed to first order, but the amount of voltage is. So that's the action of having a source resistance, which could come from bad fabrication. So we can write this out in terms of a mathematical expression that we're going to have in the end a modified expression for the current. It can be viewed either as shifting of this voltage axis or here as a rescaling of the transconductance itself, so that we don't have to deal with this internal voltage, which we cannot probe because it's internal to the device. We can look at the external voltage and then lump all the changes into a modified expression for the transconductance itself. So what this means is the amount of current you get is in general lower because of the driving potential, which is actually applied across the channel. So now let's actually look at what is limiting the the speed at which we can run this transistor. So now we're going to look at the cutoff frequency. Now in the last part we looked at what turns out to be the gain of the transistor, which is going to come up in this discussion again in a moment. So what physically is our limiting factor is the time it takes to charge the MOS capacitor. So the transient time for the current to flow into the gate, which we're going to represent here as I sub I, and for the charge to build up in the channel here. So what we need to look at is this equivalent circuit here, where we're going to look at the amount of time it takes to charge up these two equivalent capacitances. And because of the transconductance, the time it takes to establish this voltage over here actually couples into the source drain performance over here through this transconductance here, which remember here is dependent on the gate source voltage. So how long it takes to establish this tells you about the behavior of this channel. The current will flow for a transient amount of time. We'll have this I versus time, and it'll look something like this, just exponentially charging up a capacitor and then discharging it again if we apply a V gate like this. So step function in the voltage, this is the current response. So if we do the circuit analysis on this equivalent circuit and do some algebraic manipulation, we can end up with this expression here. We get a j omega times the capacitance, the depletion capacitance in the semiconductor, and then this other sort of parasitic so-called Miller capacitance. So that's composed of this CGST times 1 plus the load resistance times the transconductance, and then all of this times V gate source. So this quantity here we lump into the C Miller, and it's represented here. So now our condition for when this cutoff frequency occurs is going to be when the transistor can no longer give us any current gain. And in this configuration, this common source configuration, we need to look at the amount of current flowing through the load and compare that to the current which is going into charging up this this MOS gate structure. So let's look at that mathematically in a second. So we need to construct the expression for the current gain. So this is the I drain over the input current, which is going into charging up the gate. And the ideal current that's flowing through the load is the same current that's flowing through this loop, and thus it's given by the transconductance times V gate source. And then the current that's going into the charging of the gate is expressed here. If we take its magnitude, it means we can pull off the imaginary part there, and we get 2 pi f substituted in for omega, and then so our cutoff frequency is going to occur when this is equal to unity or 1. So then we can make this substitution, rearrange, and express the cutoff frequency for how fast we can operate this this device, and it turns out to be the transconductance over 2 pi. We can further lump these two capacitances into an effective gate capacitance, which the outside world would be able to see, because we can't, because they're added in parallel, we can't differentiate them from the outside. So we can lump these together and get an expression for the cutoff frequency. So what did we learn here? We learned that there's a threshold frequency up to which we can operate this MOSFET, which has nothing to do technically with the transit time between the source and the drain. However, it does have to do with the transconductance. And the transconductance, remember, is primarily the mobility of the channel times a few other factors. So the mobility in the channel has to do with the scattering of carriers inside this channel. However, it's distinct from the actual transit time, the physical time that it takes an electron to go from one side to the other. So really it has to do with how much current flows, which has to do with the carrier number more than it does their speed. Let's go back to the first thing we derived, which was that if you had parasitic resistances, your effective transconductance went to a smaller number. So this cutoff frequency will be lowered, and you'll reduce the bandwidth of your MOSFET if parasitic resistances are present in the equivalent circuit also. So let's just write a final equation for the ideal MOSFET and look at what happens to our cutoff frequency. So the cutoff frequency is going to be given by our transconductance. So this is the width of the channel, the mobility of the electrons in the channel, the capacitance of the oxide divided by the length of the channel, and then this is times V gate minus V threshold when we're in the saturation regime of the current voltage curve. And then down in the bottom, the lumped gate capacitance in the simplest possible case is just going to be given by the capacitance of the oxide times the width and length, just the area of the channel. So we can pull out some factors here, and in the end, we end up with mobility V gate minus V threshold over 2 pi times L squared. So in the end, the length of the channel does enter into the equation, but again, I'll highlight that it's not because of the transit time of carriers. It's actually more a geometric effect, as you can see from this expression. It has to do with the gate's ability to pull carriers into the conducting channel rather than the time it takes for them to cross. The mobility does appear in there, But this expression actually tells you a lot about why we want to make smaller and smaller MOSFETs. And it's because of this squared dependence on the channel length. So if we can shrink the channel by a factor of 2, we can speed up our MOSFETs by a factor of 4 and get more bandwidth. Also, if we can do anything to improve the mobility, we can greatly enhance the bandwidth of our MOSFETs. So in this section here, we've explored what determines the cutoff frequency of our MOSFETs. And we showed that it's actually the time it takes to charge up the gate and the time it takes to draw the electrons, in this example here of a P body MOSFET operating in inversion mode. The time it takes to draw those electrons into the channel and charge up the full gate is what determines the cutoff frequency. So we'll summarize this physics here in this little expression at the bottom, and it gives us 2 motivating factors for improving our devices in terms of the bandwidth they can handle. So the first is to make the channel mobility higher, and the second is to make the channel shorter. And these are 2 of the factors that have driven a lot of the technological advancement in MOSFETs.